So let's jump to the material of the course. Let's jump in here. Let's go to the Turing machine. Last week we went through the Turing machine. In here, I want just shortly to recap the things in a few minutes in Turing machine and then continue. As you can see, I mentioned we have discussed the finite automata, push-down automata, and then finally Turing automata. In this shape, in this image, we can compare them. In finite automata, we had we had a tape, and on the tape we have some characters, we have some states, and the head of the tape is some characters and reading toward the right. In the push-down automata, that was the same, and we had also a memory which used to be called as the push-down or stack memory. That was the first in, first out strategy for that memory. And apart from that, then we had the Turing machine, which was some differences in here. The first difference was it is infinite, the length of the tape. That means it's not like limited like these guys. And also we have the initial state, we have the state, the tape is head of the machine is on a specific character. Also, apart from that, we will have some more empty characters, like we discussed here. And then we talked about also we could have the chance of, the other difference was we could have the chance of writing on the tape, which we didn't have for the other machines. And also we could move to the left and right, but for the other machine, all the time it was moving to the right. But here we can move to left and right also. That was the differences of Turing machine. Like I said, you can have the blank or single empty on the machine. Infinitely, we can move to the left and right discussing here. And that was the way we used to show the instructions in Turing machine. If you are instead QI, receive symbol AJ on the head, and then what would happen, that was the instruction and rules. And also that could be an example of Turing machine we discussed last week. I published a video. Video needed to have some sort of refinement, so because of that I have not published that yet, but I will publish it. So, and we talk about the deterministic and non-deterministic. In deterministic Turing machine, only there is one possible moves at a specific, because you need to deterministically say what happens in here, and not saying, okay, there are lots of options, and so it is non-deterministic. No, deterministic one, only one possible moves is possible in here. And then the most important thing was the meaning of acceptance. You know, in the machine, what the main usage of the machine was actually if it can accept a specific language or not. Or let's put it another way, if it is possible to generate that language with that machine or not. Okay, so we would say, okay, this machine will accept this language or can generate this language if any string of that language is accepted by the machine. So for the other machine, the criteria for accepting the specific string was if that specific string, if we start in the initial state and reading the first symbol of the string and then moving toward the right side of the tape, and then we finish the string when we are in the final state. That was the criteria for the other machine. But for the Turing machine, and since we don't have any final state, then accepting a string is equal to if machine halts after finite number of moves. So that's a matter of if the machine halts or if it doesn't. So if for a specific string machine halts at some finite number of moves, then the string is accepted. Otherwise, it's not accepted. So for example, we went through this example and see if you want to see if this specific string ABA is accepted by this machine string with two states, this alphabet, the initial state and the instruction. And we examine that based on the different rules, and finally we say, yes, it is halted. So that means this string is accepted by the machine. Well, we applied some changes to the instruction, and we saw if we have this rule added to the instruction, it might be the situation that it never halts. So that means this Turing machine, won't accept this string. And then if this string is a string of a specific language, that means that Turing machine won't accept that specific language, right? And also we applied another change to the instruction, and again we saw it never halts. It falls into an infinite loop of reading the empty, and moving toward the right, blah blah, etc. So that's the situation when the machine won't halt, and so the machine won't accept the strings. And there's one. Yeah, and we had another concept which is situation. Situation help us, instead of plotting lots of these pictures, tapes, blah blah, etc. We can show how machine works through the string using these guys, which are called the situation. So that was the thing we talked about. And also we can have the state diagram again, similar to the machines, and it shows what will happen if you are in a specific state, receive specific symbols, and what you are going to do with that specific symbol at that specific state. For example, if you are in Q0, receive B, you will move to the right and don't change B. If this happens, that means if you are in Q0, receive A, you will move right, don't change the whatever we have in the state on the tape, and so on, right? So we can show using the state diagram, and we can analyze if the machine halts on something or if the machine accepts it or not. So, for example, for this specific machine with this instruction and with this state diagram, if we receive this specific string, it looks like we fall into this specific loop in here. If we are in Q0, if we have 3B, as soon as we receive B, we will move right, we will go to the next B, and we will rotate in here for until we get to the empty. As soon as we get to the empty, this will happen. We are in Q0, we receive empty and blank, in other words, and rotate and move right. And so that means we will halt in here. That's a trap kind of. We will halt in here, and then that means the machine never halts. So that means the string is not accepted using the Turing machine. Okay. I don't want to go through all this example. That's the thing we discussed last week. Just I wanted to show you some stuff shortly. And also we talk about the partial function in mathematics. If you remember, the partial function is a function that only is defined only on specific elements of the domain of the function. For example, this function is not defined on 1. If 1 is the input, what will happen? We don't know, because that's the function, that's the partial function. Okay. What if the input is 2 and 3, 2 and 3, and then we have some definition for that function. There we talk about that because we wanted to say Turing machine is a machine that can solve the partial function. That's interesting thing about the Turing machine. That means we can implement some stuff using the Turing machine. We can solve some problem. We can look at that as a computation machine or computer. Okay, so that's the reason why Turing machine is the beginning, is the dad, is the parent of is the dad or mom of, or parent of the computers, because using the Turing machine we can do the computation. For example, if we want to calculate the summation, that's easily can be possible. So you can say you can show the numbers n using n specific of the same symbol. For example, that shows 3 and that shows 5, and we can have a Turing machine that just do the summation. That means what is the summation of 3 and 5, which is 8. So if you receive 3 and 5 on the tape, then at the end of the day, when machine halts, you will have 8 of symbol A on the tape. That means the summation of 3 and 5 is 8. So it can go beyond, and we can have a little bit more complicated, even the functions in here, like as you can see. Okay, so like the square, the factorial, etc. And that's the beauty of this module. We are seeing how this concept have shaped actually the computings and computers, right? So that's the whole story of recursive function and one example.